Right now, somewhere in the universe, a star is being born. Somewhere else, a supernova is exploding with the light of 1 billion suns. The cosmos feels alive, vibrant, eternal, but it isn't. The universe is dying. Not quickly, not dramatically, but slowly, inevitably, over timescales so vast, they make the current age of the universe seem like a single heartbeat. Tonight, we're going to take a journey forward in time. Not millions of years, not billions. We're going trillions of years into the future, then quadrillions, then numbers so large they don't have names in everyday language. We're going to watch every star burn out, every atom decay, every black hole evaporate. We're going to witness the universe fall asleep forever. And we're going to understand what eternal silence truly means. Before we begin this journey into the deepest future, if you find these explorations of the cosmos meaningful, a quick like or subscribe would really help this channel grow. It's a small thing for you, but it makes a huge difference for me. And honestly, contemplating the end of everything makes me appreciate the present moment even more, including the fact that you're here, watching this. Now, let's begin. Let's start with something familiar. Look up at the night sky on a clear evening, away from city lights, and you'll see thousands of stars scattered across the darkness. Each one is a sun, a nuclear furnace converting hydrogen into helium, releasing energy that travels across the void to reach your eyes. Some of those photons have been traveling for hundreds of years, some for thousands. By the time they reach your retina, the stars that emitted them might have changed, moved, or even died. But you wouldn't know it yet. Light carries old news across the cosmos. The universe has been making stars for about 13.8 billion years now. In cosmic terms, we live in the stelliferous era, the age of stars. It's a time when the cosmos is bright and active, when galaxies glow with the light of hundreds of billions of suns, when new stars are being born even as old ones die. Nebulae collapse under their own gravity, igniting nuclear fusion in their cores. Massive stars explode as supernovae, seeding space with heavy elements that will become part of the next generation of stars and planets. It's a dynamic, energetic, creative time in cosmic history. This is the universe we know. This is the universe that created us. The carbon in your body was forged in the heart of a star that died before the sun was born. The iron in your blood was created in a supernova explosion billions of years ago. You are quite literally made of stardust, assembled over cosmic time into a form capable of contemplating its own origins. But the stelliferous era is not eternal. It has a beginning, and it will have an end. The lights that fill the cosmos right now will not shine forever. One by one, over timescales so vast they challenge our ability to comprehend them, the stars will go out, and they will never come back on. To understand why, we need to understand how stars are made. Stars form from clouds of gas, primarily hydrogen, that collapse under their own gravity. These clouds, called molecular clouds or stellar nurseries, can be enormous, spanning hundreds of light years across and containing enough mass to form thousands of stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such stellar nursery, actively forming new stars right now. When a region of a molecular cloud becomes dense enough, gravity takes over. The gas begins to fall inward, collapsing toward the center. As it falls, it heats up. The gravitational potential energy of the gas is converted into thermal energy, raising the temperature of the collapsing core. This process continues for hundreds of thousands of years, the core getting denser and hotter until something remarkable happens. When the core reaches about 10 million degrees, hydrogen atoms begin fusing into helium. This is nuclear fusion, the same process that powers hydrogen bombs, but controlled and sustained over billions of years. The fusion releases enormous amounts of energy, creating an outward pressure that balances the inward pull of gravity. The collapse stops, a star is born. This balance between gravity pulling inward and fusion pushing outward defines a star's life. As long as there's fuel to fuse and the balance can be maintained, the star will shine. Our sun has been doing this for about 4.6 billion years and will continue for another 5 billion or so. It's a remarkably stable arrangement, a cosmic equilibrium that can persist for eons. But here's the crucial point. There's only so much hydrogen in the universe. The Big Bang created a finite amount of matter, and while that amount is staggeringly large, it is not infinite. The observable universe contains roughly 2 trillion galaxies, each containing anywhere from a few million to a few trillion stars. The total number of stars is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros, an almost incomprehensible number, and yet it's finite. Every single one of those stars is burning through hydrogen fuel. Every fusion reaction converts 4 hydrogen atoms into 1 helium atom, releasing energy in the process, but also permanently removing that hydrogen from the available supply. Once hydrogen is fused into helium, it can't be unfused. The process is one way. Moreover, star formation itself uses up the raw material. Every time a star forms, it removes hydrogen from the interstellar medium, locking it away in a stellar core. Some of that material is returned when stars die, blown back into space by stellar winds or supernova explosions. But not all of it. Some gets locked away permanently in stellar remnants like white dwarfs and neutron stars. Some gets converted into heavier elements that are less useful for forming new stars. Galaxies are constantly using up their reserves of star-forming gas. The Milky Way, our home galaxy, forms about 1 or 2 new stars every year. That might not sound like much, but it adds up over billions of years, and we're not replenishing that gas fast enough. Gas falls into galaxies from the intergalactic medium, and galaxy mergers can bring in fresh supplies, but these processes are slowing down as the universe expands and matter becomes more spread out. The rate of star formation in the universe has actually been declining for billions of years. We're past the peak. The universe formed stars most vigorously about 10 billion years ago, during what astronomers call cosmic noon. Since then, the rate has been steadily dropping. The universe today forms about 30 times fewer stars per year than it did at its peak. We're in the late afternoon of cosmic star formation, heading toward evening. In about 100 billion years, give or take, the universe will have essentially stopped making new stars. The gas will be used up, locked away in stellar remnants, or spread so thin by the expansion of space that it can no longer collapse into new suns. This is the first great transition, the end of starbirth. After 100 billion years, no new stars will form. The universe will have to make do with the stars it already has. But even after new stars stop forming, old stars will continue to shine. For how long depends on what kind of star we're talking about. And this is where the story gets interesting, because different types of stars have vastly different lifespans. Massive stars, The giants and supergiants that blaze with tremendous luminosity burn through their fuel quickly. A star 10 times the mass of the Sun might live only 20 million years before exhausting its hydrogen and exploding as a supernova. A star 50 times the mass of the Sun might live only a few million years. These stars are like sprinters, burning bright and dying young. They're spectacular while they last, outshining a million suns, but their time in the cosmic spotlight is brief. By astronomical standards, these massive stars are already rare. They make up only a tiny fraction of all stars, and by the time the universe stops forming new stars, most of them will have long since exploded and died. The massive stars that exist at the end of the star-forming era will be among the last of their kind, the final generation of cosmic giants. Our Sun is a middleweight star. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's not particularly large or particularly small, not particularly bright or particularly dim. It's ordinary, average, unremarkable in almost every way, and that ordinariness is part of what makes it stable enough to support life. The Sun will live about 10 billion years total, and it's already about 4.6 billion years into its life. In another 5 billion years or so, it will exhaust its hydrogen fuel. When that happens, the core will contract and heat up, while the outer layers will expand enormously. The Sun will become a red giant, swelling to perhaps 100 times its current diameter, engulfing Mercury and Venus, and possibly Earth. Eventually, the red giant will shed its outer layers, creating a beautiful planetary nebula, a shell of glowing gas expanding into space. What's left behind will be the Sun's core, a dense ball of carbon and oxygen called a white dwarf. The white dwarf will glow with residual heat for billions of years, slowly cooling, but it will never generate new energy. Its fusion days will be over. Stars like the Sun are more like marathon runners than sprinters, but even marathons have finish lines. By the end of the star-forming era, in 100 billion years, most Sun-like stars will have either died or entered their final stages. The yellow and orange stars that light up the night sky today will be white dwarfs or red giants approaching their end. The real long-distance champions of the stellar world are the red dwarfs. These are small, dim stars, typically less than half the mass of the Sun. The smallest red dwarfs have only about 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. They're so small and so cool that they burn their fuel incredibly slowly. How slowly? A red dwarf with about 10% of the Sun's mass might shine for 10 trillion years. Not billion, trillion. That's roughly 1,000 times longer than the current age of the universe. The universe would have to exist for 1,000 times its current age before these stars would start to run out of fuel. Red dwarfs are also the most common type of star in the universe. About 70 to 75% of all stars are red dwarfs. Names like Proxima Centauri, our nearest stellar neighbor at just over 4 light years away, and Barnard's star, the second closest star system, are examples of red dwarfs. They're so dim that none of them are visible to the naked eye from Earth, despite being relatively close. Proxima Centauri, right next door in cosmic terms, is still invisible without a telescope, but they're everywhere, vastly outnumbering stars like our Sun. For every Sun-like star in the Milky Way, there are perhaps 10 or 20 red dwarfs. They're the silent majority of the stellar population, dim and unassuming, but incredibly long-lived. This means that long after stars like the Sun have died, long after the bright giants and supergiants have exploded and faded, the red dwarfs will still be burning. They'll be the last lights in a darkening universe. Let's jump forward in time and see what this looks like. 1 trillion years from now. The universe is about 70 times older than it is today. The cosmic landscape has changed dramatically. Star formation stopped long ago, roughly 900 billion years in the past from this vantage point. No new stars have formed for almost 1 trillion years. The raw material is simply gone, dispersed by the relentless expansion of space or locked away in stellar remnants. Galaxy mergers have combined many smaller galaxies into larger ones. The Milky Way and Andromeda merged billions of years ago, about 5 billion years after the present day, forming a large elliptical galaxy that astronomers have nicknamed Milkdromeda. Over the subsequent hundreds of billions of years, this merged galaxy has continued to evolve, consuming smaller satellite galaxies, its structure settling into a more uniform elliptical shape as the spiral arms that once defined both parent galaxies faded away. But even this merged galaxy is different from what we know. The bright blue stars that once traced the spiral arms are long gone. They burned out billions of years ago. The yellow sun-like stars followed, evolving into red giants and then white dwarfs over the next several billion years. What remains are the red dwarfs, the longest-lived stars, still patiently burning their hydrogen fuel. The universe is dimmer than it's ever been, but it's not dark yet. Red dwarfs are dim, but there are so many of them that their combined light still illuminates the cosmos. The night sky from a hypothetical planet orbiting one of these stars would be filled with faint red points of light, each one a tiny sun burning steadily against the encroaching darkness. But even red dwarfs don't last forever. As trillions of years pass, even these patient stars begin to exhaust their fuel. The larger red dwarfs, those with perhaps half the sun's mass, burn out first. They've been shining for trillions of years, but now their hydrogen is finally running low. They can't sustain fusion anymore. They cool and dim, transitioning from stars to stellar remnants. The smaller red dwarfs last longer. The smallest ones, those with just 8% of the sun's mass, can burn for tens of trillions of years. They're so miserly with their fuel, fusing hydrogen so slowly that they can stretch their supply across almost inconceivable spans of time. Let's jump forward again, 10 trillion years from now. We're now at about 700 times the current age of the universe. Most red dwarfs have finally exhausted their fuel. The universe has been dimming steadily for trillions of years, and now the end of the stelliferous era is approaching. The smallest, most efficient red dwarfs are sputtering out. One by one, the last stars are dying. Each one represents the end of a nuclear furnace that has been burning since before the star-forming era ended. Each one was born in a molecular cloud that collapsed and ignited fusion when the universe was still young, still making new stars, still in its creative phase. Now they're dying. And when they're gone, there will be no more. No new stars will rise to take their place. The fuel is exhausted. The cosmic fires are going out. Imagine being on a planet orbiting one of these final stars. What would you see? You'd see a sky that's almost completely black. The expansion of the universe has carried most galaxies beyond the observable horizon. Remember, the universe has been expanding for 10 trillion years at this point. Space has stretched enormously. Galaxies that were once visible, even nearby galaxies that were once neighbors, have been carried away by this expansion. Light from distant galaxies, redshifted by the expansion of space, has stretched to wavelengths longer than any detector could register. The cosmic microwave background radiation, already stretched to microwave wavelengths today, has stretched even further, to wavelengths billions of times longer. It's still there, filling the universe, but it carries almost no energy. It's a ghost of the Big Bang, faded almost to nothing. You'd see your own galaxy, but it would be a ghost of its former self. Instead of the bright spiral or elliptical structure that once existed, you'd see a diffuse collection of dim objects, white dwarfs that have been cooling for trillions of years, now barely visible, neutron stars, even dimmer, brown dwarfs that never quite became stars, cold and dark, and scattered among them, the last red dwarfs, still shining but barely. Your star, that final red dwarf, would appear as a dim red ember in the sky. Not bright and yellow like our sun, not even orange, just a deep, sullen red, radiating barely enough heat to warm your world. A planet in the habitable zone of such a star would orbit very close, perhaps completing a year in just a few weeks. The star would loom large in the sky, but its light would be weak, its warmth feeble, and even that ember is dying. You might watch it over generations, observing subtle changes. The star dimming, its colour shifting, its output declining, the end approaching. When a red dwarf exhausts its hydrogen, it doesn't go out with a bang. There's no supernova, no dramatic explosion. Red dwarfs are too small for that. They don't have the mass to fuse heavier elements or to collapse catastrophically. Instead, they simply cool down, transitioning from a star to a stellar remnant. What's left behind is a type of object we've never actually observed, because the universe isn't old enough for any red dwarf to have died yet. The oldest red dwarfs in the universe today are still burning, still fusing hydrogen, still in the prime of their incredibly long lives. We call the remnant they'll eventually leave behind a black dwarf. A black dwarf is essentially a white dwarf that has cooled completely, no longer emitting significant light or heat. White dwarfs are the remnants of sun-like stars, the cores left behind after the outer layers are shed. They're incredibly dense, with the mass of a star compressed into a volume the size of Earth. They glow with residual heat when they form, but they have no internal energy source. They slowly cool over time. The remnants of red dwarfs would be different in some ways. They'd be smaller, because red dwarfs are smaller. They'd be made primarily of helium, because red dwarfs are fully convective, meaning their material is constantly mixed throughout the star. Unlike sun-like stars, which develop distinct layers with hydrogen in the outer regions and helium in the core, red dwarfs mix their fuel uniformly. When they finally exhaust their hydrogen, the entire star has been converted to helium. But the end result is similar. A cold, dark ball of degenerate matter slowly cooling toward absolute zero, not emitting any significant light or heat, just existing, a remnant of what once was, drifting through the void. 100 trillion years from now, this is approximately the end of the stelliferous era. The last stars have burned out. The universe, which once blazed with the light of hundreds of sextillion stars, has gone dark. Let me try to help you visualize this transition, this immense journey from cosmic noon to eternal night. For the first 13.8 billion years of the universe, we've been in the equivalent of cosmic morning. The sun is rising, so to speak. Stars are forming, galaxies are growing, complexity is increasing. Heavy elements are being created in stellar cores and distribute by supernova explosions. Planets are forming, and on at least one planet, life has arisen and developed intelligence. We're in the bright, vibrant, active phase of cosmic history. The Stelliferous era, which will last until about 100 trillion years, is like a very long day. Most of this day is still ahead of us. We're only about 1/10,000th of the way through it. The universe will continue to shine with starlight for roughly 10,000 times longer than it has existed so far. That's an almost incomprehensible span of time still ahead. But eventually, evening comes. The rate of star formation has already peaked and begun to decline. In 100 billion years, it will stop entirely. The last generation of stars will be born and then no more. The universe will enter its twilight phase, still lit by existing stars but no longer creating new ones. Over the next trillions of years, those existing stars will die, one by one. The massive stars go first, within millions of years of their birth. Sun-like stars follow over billions of years. Red dwarfs persist for trillions. The universe dims slowly, like a sunset that lasts for eons. Colours shift from blue and white to yellow to orange to red, as hotter stars die and only cooler ones remain. And finally, the last red dwarf exhausts its fuel. The last nuclear fire goes out. The cosmic sunset ends. And what follows is night. Except this night will never end. There will be no sunrise, no new day. The universe has used up its fuel for making stars. The raw material is gone, dispersed, locked away. The lights that once filled the cosmos will never turn on again. This is a profound change, the most fundamental transition in the history of the universe. For 100 trillion years, the cosmos has been defined by stars, by the light they emit, the energy they generate, the elements they create, the processes they drive. Stars have been the engines of cosmic evolution, the sources of almost everything interesting that has happened since the Big Bang. And now, they're gone. The universe must continue without them, into a future that will be fundamentally different from everything that came before. But the end of the Stelliferous era is not the end of the universe's story. It's more like the end of the first chapter. The chapters that follow are longer, stranger, and ultimately darker than anything we've discussed so far. Even after the stars are gone, there's still matter in the universe. There are still objects, remnants of what once was. White dwarfs, slowly cooling toward absolute zero. Neutron stars, the ultra-dense cores of massive stars that exploded as supernovae. Black holes, regions of space-time so warped that nothing can escape. Brown dwarfs that never quite became stars in the first place. Rogue planets, drifting through the void, frozen and dead but still existing. The universe isn't empty, it's just dark, and for a very, very long time these remnants will persist. They'll drift through space, occasionally encountering each other, occasionally merging or being captured, but mostly just existing, slowly cooling, slowly decaying, waiting for what comes next. Because these remnants won't last forever either. Nothing lasts forever. And as we continue forward in time, as we leave the Stelliferous era behind and enter what physicists call the degenerate era, we'll see even these remnants slowly, inexorably fade away. The death of the stars is just the beginning of the universe's journey into darkness. What follows will make the Stelliferous era look like a brief flash of light, a momentary illumination before the true night begins. Before we move on, let's pause and appreciate what this means. Right now, you're alive during the Stelliferous era. You exist in the brief cosmic moment when stars shine, when galaxies glow, when the universe is filled with light and energy and complexity. From the perspective of deep time, this era is extraordinarily short. The universe will be dark for far, far longer than it will be bright. Think about that. The total duration of starlight in the universe, from the first stars that formed a few 100 million years after the Big Bang, to the last red dwarfs that will burn out in about 100 trillion years, is roughly 100 trillion years. That sounds like a long time, and it is. But compared to what comes after, it's nothing. The universe will spend far more time in darkness than in light. Far more time cold than warm. Far more time empty than full. This stelliferous era is a brief candle flame in an infinite night, a momentary spark in an eternal void. And you're here to see it. You're witnessing the universe in its youth, its prime, its brief, flowering before the long autumn and endless winter that follow. Every sunrise you see, every star you glimpse in the night sky, every photon of light that reaches your eye from a distant sun is a gift of this particular cosmic moment. The stelliferous era will end. The stars will go out. And the universe will enter a darkness that makes our current night sky look blazingly bright by comparison. But that's still far in the future. For now, the stars still shine. The cosmos is still alive with light and energy and change. And we're here to see it, to wonder at it, to try to understand it. The next phase of our journey will take us into the degenerate era, when the remnants of stars slowly cool and, eventually, the very atoms they're made of begin to fall apart. The timescales will grow even larger. The changes will become even more profound. And the universe will continue its slow, patient journey toward its final state. But that's for the next part of our story. For now, let's appreciate the light while it lasts. The stars are gone. Every single one of them. Let that statement settle into your mind for a moment. Every star that ever existed. From the very first generation that ignited a few 100 million years after the Big Bang, to the last stubborn red dwarfs that burned for trillions of years, has exhausted its fuel and gone dark. The nuclear fires that lit the cosmos for 100 trillion years have finally, permanently gone out. The universe has entered what physicists call the degenerate era. And despite its somewhat negative-sounding name, this era is not about moral decline. The name comes from the type of matter that dominates this age. Degenerate matter is matter that has been compressed so tightly that quantum mechanical effects prevent it from collapsing further. It's held up not by heat or pressure in the normal sense, but by a fundamental principle of quantum physics called the Pauli exclusion principle. White dwarfs and neutron stars are made of degenerate matter. In white dwarfs, it's electron degeneracy pressure that holds the star up against gravity. Electrons, being fermions, refuse to occupy the same quantum state as other electrons. Pack them tightly enough, and this refusal creates an outward pressure that can support an entire star's worth of mass. In neutron stars, it's neutron degeneracy pressure doing the same job at even higher densities. These aren't like normal matter. They're exotic, incredibly dense, and remarkably stable. A white dwarf can sit in space for eons, neither collapsing further nor expanding. It's in a kind of quantum mechanical equilibrium, a frozen state maintained by the fundamental properties of particles themselves. Or at least they seem stable. In the degenerate era, we'll discover that even the most stable-seeming objects in the universe are slowly, inexorably, breaking down. Nothing lasts forever. Not even matter itself. Let's take stock of what exists in the universe at this point. 100 trillion years have passed since the Big Bang. The cosmic inventory is remarkably different from what we know today. White dwarfs are everywhere. The remnants of sun-like stars that shed their outer layers and left behind dense cores of carbon and oxygen. They're slowly cooling toward absolute zero, radiating away the heat they accumulated during their formation. There are neutron stars too, the ultra-dense cores of massive stars that exploded as supernovae. These spinning remnants are also cooling and spinning down, their once powerful magnetic fields decaying over the eons. Black dwarfs have joined the population, the cooled remnants of the smallest red dwarfs. These are essentially balls of helium that will never generate energy again. They've never existed in the current universe because no red dwarf has had time to die yet, but by 100 trillion years, they're common. Brown dwarfs drift through space, objects that never quite became stars. With masses, between large planets and small stars, they generate some heat through gravitational contraction, but never achieved sustained nuclear fusion. Now they're slowly cooling, indistinguishable from very large planets. Rogue planets number in the trillions upon trillions, worlds that were ejected from their solar systems by gravitational interactions and now drift through the void. Their surfaces are frozen, their atmospheres long since liquefied and frozen onto the ground. Their interiors are slowly cooling as heat conducts outward into the emptiness. And there are black holes. Stellar mass black holes form from the collapse of massive stars. Supermassive black holes that once sat at the centers of galaxies, having grown enormous through billions of years of feeding. These regions of space where gravity has become so strong that nothing can escape represent a different category entirely. They're not made of matter in the conventional sense. They're made of warped space-time itself. This is the universe of the degenerate era. Dark, cold, filled with remnants of what once was. No new stars are forming because there's no gas left to form them. No new energy is being generated in significant amounts because fusion has stopped everywhere. The universe is slowly, patiently winding down. But the degenerate era is not static. Things are still happening. Processes are still unfolding. It's just that these processes operate on timescales so long, they make the entire stelliferous era look like a camera flash in a dark room. Let's talk about white dwarfs in more detail, since they're among the most common stellar remnants. Understanding their fate helps us understand the fate of matter itself. A white dwarf is about the size of Earth, but has roughly the mass of the Sun. This means an incredible density. A teaspoon of white dwarf material would weigh about 5 tons on Earth. You couldn't lift it. You couldn't even budge it. The electron degeneracy pressure that holds the white dwarf up creates matter so dense that it defies everyday intuition. When a white dwarf first forms, it's incredibly hot. Surface temperatures can exceed 100,000 degrees Fahrenheit, far hotter than the surface of the Sun. The core is even hotter. This heat is the residual energy from the star's formation, from the gravitational collapse that created the white dwarf in the first place. All that gravitational potential energy was converted to heat, and now the white dwarf is slowly radiating it away. But white dwarfs have no internal energy source. They're not generating heat through fusion like main sequence stars. They're simply cooling down, like a hot coal removed from a fire. The heat flows outward, radiates into space, and the white dwarf gets cooler. The cooling process is slow, astronomically slow. A white dwarf takes about 1 billion years to cool from its initial formation temperature to about 10,000 degrees Fahrenheit, roughly the temperature of our sun's surface. After about 10 billion years, it might cool to around 5,000 degrees. The oldest white dwarfs in the universe today, formed perhaps 12 billion years ago, have cooled to temperatures of around 4,000 degrees, giving them a reddish glow, but as a white dwarf gets cooler, it cools more slowly. The rate of heat loss depends on temperature. A very hot object radiates energy much faster than a warm object. So as white dwarfs approach lower temperatures, their cooling rate decreases. The approach to absolute zero becomes asymptotic, slower and slower, but never quite reaching it. At the start of the degenerate era, 100 trillion years in the future, most white dwarfs have been cooling for tens of trillions of years. They're no longer hot. They're no longer even warm by any reasonable definition. They've approached absolute zero, though they'll never quite reach it because quantum mechanics forbids reaching exactly zero temperature. They become black dwarfs. Not black holes, which are something entirely different, but black dwarfs. Dark spheres of crystallized carbon and oxygen, utterly cold and utterly dark. They emit no significant light. They produce no significant heat. They're just there, frozen monuments to stars that died long ago. Something fascinating happens as white dwarfs cool to these extreme temperatures. Their interiors crystallize. The carbon and oxygen atoms, held in place by electron degeneracy pressure but free to arrange themselves within that constraint, begin to organize into a regular lattice structure. The white dwarf solidifies from the inside out. A white dwarf becomes, essentially, a giant diamond in space, not metaphorically, literally. The crystalline structure of carbon under these conditions is similar to diamond. An Earth-sized, sun-mass diamond floating in the darkness of space, completely dark, completely cold, and incredibly beautiful if anyone were there to appreciate it. Astronomers have actually detected evidence of this crystallization in white dwarfs that exist today. The process releases a small amount of heat as the atoms settle into their crystalline positions, and this heat slightly slows the cooling rate. We've observed white dwarfs that are cooling more slowly than expected, and crystallization is the explanation. Neutron stars undergo a similar process of cooling, though their internal structure is even more exotic. A neutron star is the collapsed core of a massive star, compressed to such incredible density that protons and electrons have emerged into neutrons. The entire mass of a star larger than our Sun is crushed into a sphere about 12 miles across. A teaspoon of a neutron star material would weigh about 1 billion tons. To put that density in perspective, if you took Mount Everest and compressed it to the density of a neutron star, it would fit in a space smaller than a grain of sand. The matter is so dense that if you could somehow survive on the surface of a neutron star, you weigh about 100 billion times what you weigh on Earth. The gravitational field is so strong that light leaving the surface is noticeably redshifted. Neutron stars are born spinning rapidly. The conservation of angular momentum ensures this. Just as a figure skater spins faster when they pull their arms in, a collapsing stellar core spins faster as it shrinks. A massive star's core might rotate once every few weeks. Compress that core to a 12-mile sphere, and it might spin dozens of times per second. Neutron stars also have incredibly strong magnetic fields, often trillions of times stronger than Earth's magnetic field. These magnetic fields interact with the surrounding space, producing beams of radiation that sweep across the sky like lighthouse beams. When these beams happen to point toward Earth, we detect the neutron star as a pulsar, a cosmic lighthouse blinking with remarkable regularity. But neutron stars don't spin forever. Their rotation slows down over time as energy is radiated away through those same magnetic fields. The spinning magnetic field generates electromagnetic radiation, and that radiation carries away energy and angular momentum. After about 10 million to 100 million years, most neutron stars have slowed to the point where they no longer produce detectable pulsar signals. After trillions of years, they've slowed to a crawl, rotating perhaps once every few hours, once every few days. Their magnetic fields have decayed, weakened by the same processes that slowed their spin. They're cold, dark, and silent. No longer the violent, energetic objects they were when they formed, just dense balls of neutrons, slowly approaching thermal equilibrium with the cold universe around them. Brown dwarfs have their own story in the degenerate era. These are objects that never quite became stars. They formed from collapsing gas clouds, just like stars, but they didn't have enough mass to achieve sustained hydrogen fusion in their cores. The minimum mass for hydrogen fusion is about 8% of the Sun's mass, roughly 80 times the mass of Jupiter. Brown dwarfs fall below this threshold. When a brown dwarf forms, it's warm. The gravitational collapse that created it released energy, heating the object to temperatures of perhaps 2,000 to 3,000 degrees. Some of the largest brown dwarfs might briefly fuse deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than regular hydrogen. But this deuterium burning doesn't last long, and it doesn't significantly affect the brown dwarf's evolution. Without sustained fusion, a brown dwarf simply cools over time. It radiates away its formation heat, getting dimmer and cooler as the eons pass. After trillions of years, a brown dwarf becomes indistinguishable from a very large planet. Cold, dark, drifting through space without purpose. The line between brown dwarfs and giant planets becomes completely blurred. In the degenerate era, both are cold, both are dark, both are made of similar materials. The only difference is their history, whether they formed from a collapsing gas cloud like a star, or accreted around a core in a protoplanetary disk, like a planet. And that historical difference is impossible to determine when all the evidence has cooled to the same temperature. Rogue planets are perhaps the most numerous objects in the degenerate era. During the stelliferous era, gravitational interactions in young solar systems frequently ejected planets. Close encounters with other planets, passing stars, or orbital instabilities sent worlds flying off into interstellar space. Some estimates suggest there might be more rogue planets in the Milky Way than stars, perhaps trillions of them drifting through the darkness. Without a star to warm them, these rogue planets froze almost immediately after ejection. Any atmosphere they might have had liquefied and then froze onto the surface. Any oceans turned to ice. Any geological activity slowly wound down as internal heat radiated away. In the degenerate era, 100 trillion years later, even the largest rogue planets have completely frozen. Their interiors are as cold as their surfaces. There's no heat left, no energy, no activity. They're frozen worlds, monuments to solar systems that existed and then came apart, drifting silently through an expanding universe that barely notices their presence. This is the degenerate era in its early phases. Dark remnants slowly cooling toward absolute zero. It sounds peaceful, in a way. Quiet. The tumult of the stelliferous era, with its exploding supernovae and colliding galaxies, is over. Now there's just the slow, patient dissipation of stored heat into the ever-expanding void. But even this isn't truly stable. Even these remnants, these crystallized white dwarfs, and frozen planets and silent neutron stars will not last forever. Because the degenerate era brings something new, something that attacks the very foundation of matter itself. This brings us to one of the most profound predictions of modern physics: proton decay. And to understand why proton decay matters so much, we need to understand what protons are and what their potential instability means for everything. Protons are one of the fundamental building blocks of ordinary matter. Along with neutrons, they make up the nuclei of atoms. The number of protons in a nucleus determines what element an atom is. 1 proton makes hydrogen, 6 protons make carbon, 26 make iron, 92 make uranium. Everything you see around you, everything you've ever touched or tasted or breathed, is made of atoms built around protons. Your body contains roughly 7 octillion protons. That's a 7 followed by 27 zeros. Every cell, every molecule, every protein and DNA strand in your body depends on protons holding atoms together. Without protons, matter as we know it simply couldn't exist. For a long time, physicists believed protons were absolutely stable. Unlike neutrons, which decay into protons after about 15 minutes when they're outside a nucleus, protons were thought to last forever. The conservation laws of physics, particularly the conservation of baryon number, seem to forbid proton decay. A proton is a baryon, and if baryon number is conserved, a proton can't decay into non-baryonic particles. But in the 1970s, physicists began developing grand unified theories, ambitious theoretical frameworks that attempt to unify 3 of the 4 fundamental forces: the strong nuclear force, the weak nuclear force, and the electromagnetic force. These theories treat these 3 forces as different aspects of a single underlying force that was unified in the extremely high energies of the early universe. As physicists worked out the mathematics of these theories, they discovered something remarkable and troubling. Grand unified theories predicted that protons should decay, not quickly, incredibly slowly, but eventually. The mechanism involves particles called X bosons and Y bosons, hypothetical force carriers that mediate interactions between quarks and leptons. These bosons are incredibly massive, which is why we don't see their effects at everyday energies. But through quantum tunneling, a process that allows particles to bypass barriers they couldn't classically overcome, protons can occasionally interact with these virtual bosons and decay. The predicted lifetime of a proton varies depending on which grand unified theory you use. Different theories make different predictions based on their specific mathematical structures. But most estimates put the proton lifetime somewhere between 10 to the 34th power years and 10 to the 41st power years. Let's use 10 to the 37th power years as a rough middle estimate. That's a 1 followed by 37 zeros. Written out fully, it's 10 trillion years. Let me try to put this number in some kind of perspective, though I warn you, it defies easy comprehension. The current age of the universe is about 13.8 billion years, or roughly 1.4 times 10 to the 10th power years. The time until proton decay becomes significant is about 10 to the 27th power times longer than the current age of the universe. Here's another way to think about it. If the entire history of the universe so far, all 13.8 billion years of it, were compressed into a single second, Then the proton decay timescale would be longer than 10 trillion years. That's still so long that the comparison barely helps. Or, consider this. The Stelliferous era lasts about 100 trillion years. If the Stelliferous era were 1 second, the proton decay timescale would be about 3 billion years. We're dealing with timescales that make the entire age of stars seem like the blink of an eye. We haven't observed proton decay yet. Experiments have been running for decades, watching enormous tanks of ultra-pure water for the telltale signature of a proton falling apart. The Super Kamiokande detector in Japan contains 50,000 tons of water, surrounded by light detectors waiting to catch the flash of radiation that would signal a proton's death. So far, nothing. After years of watching octillions of protons, not a single decay has been observed. This puts a lower limit on the proton's lifetime. We know it's at least 10 to the 34th power years, probably longer. Some theories that predicted shorter lifetimes have been ruled out by these experiments, but most physicists still believe proton decay will eventually occur. The grand unified theories that predict it are too elegant, too successful in other ways, to be completely wrong. And even if protons don't decay through the specific mechanisms these theories propose, other processes might eventually destroy them. What happens when a proton decays? The exact products depend on the mechanism, but in most models, a proton decays into lighter particles. A common prediction is that a proton decays into a positron, the antiparticle of the electron, and a neutral pion. The pion is unstable and quickly decays into 2 gamma rays. The positron eventually encounters an electron somewhere in the universe and annihilates, producing more gamma rays. The net result is that the mass of the proton, about 938 million electron volts of energy, is converted entirely into radiation. The proton is gone. The matter it was part of is diminished, and a tiny flash of gamma radiation disperses into the void. What does this mean for the degenerate era? Everything. Every white dwarf, every neutron star, every black dwarf, every rogue planet, every asteroid and dust grain in the universe is made of protons. And if protons decay, then all of this matter will eventually disappear. Not quickly. On human timescales, proton decay is utterly negligible. Your body contains about 7 octillion protons. With a half-life of 10 to the 37th power years, you'd expect about 1 proton in your body to decay every 30 trillion years. You're not going to notice that. Even over the entire lifetime of a star, proton decay has essentially no effect. Even on the timescale of the Stelliferous era, 100 trillion years, proton decay is insignificant. The half-life of a proton is so long that over 100 trillion years, only a vanishingly small fraction of protons will have decayed. The white dwarfs and neutron stars and planets that exist at the end of the Stelliferous era will still be there, essentially unchanged in composition, when the last star dies, but not forever. Nothing is forever. And in the degenerate era, time stretches out so far that even the infinitesimally slow process of proton decay becomes significant. Let's jump forward to 10 to the 37th power years. This is approximately 1 half-life for protons. About half of all the protons that existed at the end of the Stelliferous era have now decayed. The white dwarfs are not what they were. They've lost half their mass, not through any visible process, but through the invisible quantum mechanical decay of their constituent protons. One by one, over eons beyond counting, protons have spontaneously disintegrated, converting themselves into radiation that escaped into space. The white dwarf is still there, still a crystallized ball of carbon and oxygen held together by gravity and electron degeneracy pressure. But it's smaller now, less massive. The decay products, the positrons and gamma rays, and eventually photons, don't stay inside the remnant. They radiate away, carrying mass energy into the void. The process continues. Another half-life passes, 10 to the 37th power years more. Half of the remaining protons decay. The white dwarf has lost 3/4 of its original mass now. It's shrinking, evaporating, dissolving into radiation so slowly that no observation could detect the change. Each half-life, the remnant loses half of whatever protons remain. After 10 half-lives, only about 1,000th of the original protons survive. After 20 half-lives, only about 1/1,000,000th. The white dwarf is barely there now, a ghost of what it once was, still held together by the same physics but containing only a tiny fraction of the matter it started with. Let's jump to 10 to the 40th power years. This is roughly 1,000 times longer than the proton half-life. By now, virtually every proton that once existed has decayed. Not half, not most, but essentially all of them. The white dwarfs are gone. Completely gone. Every carbon atom, every oxygen atom has come apart as its constituent protons spontaneously disintegrated. The electron degeneracy pressure that held these structures together has nothing left to hold. The matter has evaporated into radiation. The neutron, stars are gone too. This might seem surprising since neutron stars are made of neutrons, not protons. But neutrons outside a nucleus are unstable, decaying with a half-life of about 15 minutes. Inside a nucleus, neutrons can be stable, protected by the nuclear binding energy. In a neutron star, the situation is more complex, but the extreme conditions don't protect against the fundamental instability of baryonic matter. If protons decay, the processes that cause proton decay likely affect neutrons too, just through slightly different channels. The black dwarfs are gone, the rogue planets are gone, the asteroids are gone, the dust is gone. Everything made of ordinary matter has evaporated away, converted into radiation over a timescale so long that the human mind cannot truly grasp it. What's left? The decay products have long since dispersed. The gamma rays produced by proton decay have been redshifted by the expansion of the universe, stretched to wavelengths far longer than anything we could detect. They're still there, a faint bath of radiation permeating all of space, but they carry almost no energy. They're the diluted remnants of all the matter that once was. Neutrinos are everywhere too. Produced by various decay processes over the eons, these ghostly particles barely interact with anything. They pass through matter as if it weren't there. Now, with no matter left to pass through, they simply stream through the void, occasionally interacting with nothing at all. And there are electrons and positrons scattered through space, the remnants of atomic electrons that were released when their parent atoms disintegrated. These particles will eventually find each other and annihilate, producing more gamma rays. But the universe is so vast and so empty that this process takes an incredibly long time. Two electrons, or a positron and electron, might drift for eons before encountering each other by chance. But one category of objects remains: black holes. The black holes are still there. This is a crucial point, a fundamental distinction that will define the next era of cosmic history. Black holes are not made of protons. A black hole is not a ball of matter, not a collection of atoms or particles. It's a region of space-time so warped by concentrated mass that nothing can escape from inside its event horizon. The matter that fell into a black hole, whether it was hydrogen gas or stars or planets or other black holes, has been compressed beyond recognition. It's been crushed toward a singularity, a point of theoretically infinite density where our understanding of physics breaks down. Whatever protons were in that matter are no longer protons in any meaningful sense. They've been destroyed, transformed, converted into pure space-time curvature. This means black holes don't decay through proton decay. They're immune to this process. While all the white dwarfs and neutron stars and planets were slowly evaporating away over 10 to the 40th power years, the black holes remained unchanged, impassive, untouched by the decay of matter around them. In the universe of 10 to the 40th power years, black holes are essentially the only significant structures left. Stellar mass black holes, with masses ranging from a few times to a few tens of times the mass of the Sun, drift through space. Supermassive black holes, with masses of millions to billions of solar masses, sit where galaxies used to be. Intermediate mass black holes, with masses between these extremes, exist in uncertain numbers. These black holes are the last remnants of the stelliferous era, the last structures that preserve any memory of the age of stars. They formed from matter, from collapsing gas and dying stars, but they're no longer made of matter. They're made of something more fundamental, of space-time itself, twisted beyond recognition. But black holes have their own form of decay. It's slower than proton decay, much slower, but it's there. Stephen Hawking predicted it in 1974, and while it's never been directly observed because the effect is so small, the theoretical foundations are solid. Black holes radiate. They emit particles through a quantum mechanical process that slowly, incredibly slowly, reduces their mass. Eventually, given enough time, black holes evaporate completely. They vanish in a final burst of radiation, leaving nothing behind. This is what awaits the universe after proton decay has eliminated ordinary matter. The black hole era. An era dominated by these strange objects, these wounds in space-time, these last repositories of concentrated mass energy. An era that will last even longer than the degenerate era, even longer than proton decay needed to dissolve all matter. Before we move on, let's pause and contemplate the scale of what we've just described. The degenerate era lasted from about 100 trillion years to about 10 to the 40th power years. That's a span of time so vast that the stelliferous era, which seemed so immensely long, is nothing compared to it. If you represented the stelliferous era 100 trillion years as 1 second, the degenerate era would last about 3 billion years. The entire age of stars, from the first generation to the last red dwarfs, compressed in the duration of a heartbeat, compared to the slow dissolution of matter in the degenerate era. During this immense span of time, the remnants of stars slowly cooled, reaching temperatures barely above absolute zero. Their crystalline structures persisted for eons, diamond spheres floating in an expanding void. And then, so slowly that no observation could ever detect it, they began to dissolve. Proton by proton, atom by atom, matter fell apart. The building blocks of everything disintegrated into radiation. It's a process of gradual dissolution, of matter itself coming undone. Not through any violent process, not through collision or explosion, but through the fundamental instability of particles themselves. The universe patiently dismantles everything that ever existed. converting it all into the most dilute form of energy, spreading it across an ever-expanding void. And yet, compared to what comes next, the degenerate era is brief. The black hole era will last even longer. So much longer that even the immense span of proton decay becomes a footnote, a brief transition between the age of stars and the age of darkness. The universe is patient. It has all the time in the world, literally all the time that will ever exist, and it uses that time to slowly, methodically dismantle everything that once was, approaching ever closer to its final state. The state of maximum entropy. The state of heat death. The final silence that awaits at the end of time. The black holes remain. For now, they're the last structures in an otherwise empty cosmos, but they too will eventually fade. They too will eventually vanish. And when they do, the universe will enter its final era, an era from which there is no return, an era that will last not for trillions or quadrillions of years, but forever. The protons are gone, every single one of them. Let that statement wash over you for a moment and consider what it truly means. Every proton that ever existed, every building block of every atom of every star and planet and person that ever was, has decayed into energy and radiated away. Matter, in the conventional sense, no longer exists in the universe. The white dwarfs that once sparkled like frozen diamonds scattered across the void have evaporated. The neutron stars, those impossibly dense remnants of stellar violence, have dissolved. The frozen planets, the asteroids, the dust, the molecules, the atoms themselves, all of it has come apart at the most fundamental level. Proton by proton, over timescales so vast that the entire stelliferous era seems like a single heartbeat. Everything made of ordinary matter has vanished into radiation. The universe at 10 to the 40th power years is unrecognizable. If you could somehow transport yourself there, you would find yourself floating in an emptiness so profound that it defies description. No stars to light your way. No planets to stand on. No atoms to breathe. Just space, expanding endlessly in all directions, filled with nothing but the faintest whisper of radiation, the diluted remnants of everything that once was. But the universe is not entirely empty. Something remains. Something that has endured through the death of stars and the decay of matter. Something that will persist for eons yet to come. Black holes remain. Black holes are strange objects. Actually, calling them objects at all is somewhat misleading. They're not really things in the usual sense of the word. A black hole is a region of space-time where gravity has become so overwhelmingly strong that nothing can escape. Not matter, not light, not information itself. Once something crosses the boundary of a black hole, called the event horizon, its fate is sealed. It will inevitably fall toward the center, toward a point of theoretically infinite density called the singularity. To understand black holes, you need to understand what gravity really is. In Einstein's general theory of relativity, gravity isn't a force in the traditional sense. It's the curvature of space-time caused by mass and energy. When you feel your feet pressed against the floor, you're not being pulled down by a force. You're following the curved geometry of space-time created by Earth's mass. Near a black hole, this curvature becomes extreme. Space-time is so warped that all paths, even the path of light rays, curve inward toward the center. The event horizon is the surface where this curvature becomes total, where space-time is bent so severely that every possible path leads inward. Once you cross that boundary, returning would require traveling faster than light, which is impossible. You could point your spaceship directly away, from the black hole and fire your engines at full power, and you would still fall inward. The geometry of space-time itself wouldn't allow any other outcome. The event horizon isn't a physical surface. You couldn't touch it or stand on it. It's a boundary in space-time, a mathematical surface that marks the point of no return. If you were falling into a large black hole, you might not even notice when you crossed it. There would be no sign, no barrier, no flash of light. One moment you'd be outside, theoretically able to escape. The next moment you'd be inside, doomed to fall toward the singularity. And you might not even realize the transition had occurred. From the outside, a black hole appears as a perfectly black sphere, a region of absolute darkness against the background of space. It absorbs all light that falls on it and emits nothing. Black holes are invisible in the most literal sense. You cannot see them directly. You can only detect them through their gravitational effects on nearby matter or through the radiation emitted by material spiraling into them. During the stelliferous era, black holes formed in several ways. Stellar mass black holes, with masses ranging from about 5 to perhaps 100 times the mass of the Sun, formed when massive stars died. When a star more than about 20 times the mass of the Sun exhausts its nuclear fuel, its core can no longer support itself against gravity. The core collapses in a fraction of a second, crushing matter to incredible densities. If the core is massive enough, nothing can stop the collapse. The matter falls inward past its own event horizon, and a black hole is born. This process is usually accompanied by a supernova explosion. The outer layers of the star, no longer supported by the core, come crashing inward. They hit the collapsed core and bounce off, creating a shockwave that blows the star apart. The supernova can briefly outshine an entire galaxy, blazing with the light of 10 billion suns. But at the center, hidden within the expanding debris cloud, a black hole quietly forms. Supermassive black holes are something else entirely. These monsters have masses ranging from millions to billions of times the mass of the Sun. They sit at the centers of most large galaxies, including our own Milky Way. The black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. It's a relatively modest example. Some supermassive black holes contain tens of billions of solar masses. We're not entirely sure how supermassive black holes formed. They might have grown from smaller black holes that merged and accreted matter over billions of years. Or they might have formed directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar phase entirely. Some combination of both processes was probably involved. What we do know is that supermassive black holes played a crucial role in galaxy formation and evolution. The energy released by matter falling into these black holes influenced the growth of galaxies around them. Jets of material ejected from near the event horizon could travel millions of light years, affecting gas clouds far from the black hole itself. In a sense, supermassive black holes were the hearts of galaxies, pumping energy through their cosmic hosts. By the time we reach 10 to the 40th power years, when proton decay has destroyed all ordinary matter, these black holes have been around for a very long time. And they've been busy. Over the preceding eons, black holes consumed whatever fell into them. During the stelliferous era, they grew by accreting gas and swallowing stars. During the degenerate era, they continued to grow, though more slowly as matter became scarcer. Black holes merged with other black holes when their host galaxies collided and merged. Each merger produced gravitational waves, ripples in space-time that carried away some energy but left behind a larger black hole. The supermassive black holes have grown truly enormous. Galaxy mergers over trillions of years combined multiple supermassive black holes into single, even more massive objects. Some of these monsters now contain trillions of solar masses, having consumed significant fractions of their host galaxies over the eons. But now there's nothing left to consume. The ordinary matter is gone, dissolved by proton decay into radiation that is dispersed into the void. The black holes are alone in an ever-expanding universe, separated by vast distances that continue to grow as space itself stretches. This is the black hole era. An era dominated by these strange objects, these wounds in the fabric of space-time. An era that will last far, far longer than everything that came before. Now, here's the remarkable thing that defines this era. Black holes are not eternal. Despite appearing permanent, despite being made of warped space-time rather than matter, black holes can and will decay. The mechanism is called Hawking radiation, named after the brilliant physicist Stephen Hawking, who predicted it in 1974. Hawking radiation is one of the most beautiful and profound discoveries in theoretical physics. It arises from the intersection of quantum mechanics and general relativity, two theories that usually operate in completely different domains. Quantum mechanics describes the behavior of particles at the smallest scales. General relativity describes gravity and the curvature of space-time at the largest scales. They don't usually interact in ways we can observe. But near the event horizon of a black hole, they combine to produce something remarkable. To understand Hawking radiation, you need to understand something about the quantum vacuum. Empty space, according to quantum mechanics, is never truly empty. The uncertainty principle, one of the foundational rules of quantum mechanics, ensures that energy can never be precisely zero anywhere. Instead, the vacuum seethes, with activity at the smallest scales. Pairs of virtual particles constantly pop into existence and then annihilate each other, existing for only the briefest instant. These virtual particles come in pairs, a particle and its antiparticle. They appear spontaneously from the vacuum, borrow energy from the uncertainty principle for a fleeting moment, and then recombine and vanish. This happens everywhere in the universe, all the time. In the room where you're sitting right now, countless pairs of virtual particles are appearing and disappearing every second. Normally this has no effect on anything macroscopic. The particles exist for such a short time that they have no measurable impact. But near a black hole's event horizon, something strange can happen. A pair of virtual particles can form such that one particle falls into the black hole while the other escapes. Normally, virtual particles must recombine quickly because they've borrowed energy that must be repaid. But if one particle crosses the event horizon before they can recombine, the other particle is freed. It becomes a real particle, carrying away real energy into space. But that energy has to come from somewhere. You can't create energy from nothing. The energy that the escaping particle carries away must come from the black hole itself. The process effectively reduces the mass of the black hole slightly. From a distance, it appears as though the black hole is emitting radiation. This is Hawking radiation. The black hole glows, not because anything is escaping from inside the event horizon, but because quantum effects near the event horizon create particles that carry away the black hole's mass. Very slowly, the black hole shrinks. Very slowly, it evaporates. The temperature of this radiation depends on the mass of the black hole, and the relationship is inverse. Smaller black holes have higher temperatures and radiate faster. Larger black holes have lower temperatures and radiate more slowly. A stellar mass black hole with perhaps 10 times the mass of the Sun has a Hawking temperature of about 60 billionths of a degree above absolute zero. That's incredibly cold, far colder than the cosmic microwave background radiation that fills the universe today. At this temperature, the black hole emits radiation at such a minuscule rate that it would take an unimaginably long time to lose any noticeable mass. How long? For a black hole of 10 solar masses, the evaporation time is approximately 10 to the 67th power years. That's a 1 followed by 67 zeros. Written out in words, it would be 10 million trillion years. This number is so large that it defies easy comprehension. Let me try to put it in perspective. The current age of the universe is about 13.8 billion years. The Siluriferous era will last about 100 trillion years. The degenerate era, during which proton decay destroys ordinary matter, lasts until about 10 to the 40th power years. And a single stellar mass black hole will last until 10 to the 67th power years. The ratio between the degenerate era and the stellar black hole lifetime is about 10 to the 27th power. If the entire degenerate era were compressed into 1 second, a stellar mass black hole would last about 30 billion years after that second ended. But here's where it gets even more extreme. Stellar mass black holes are not the largest black holes. The supermassive black holes at the centers of galaxies are millions to billions of times more massive. And because larger black holes radiate more slowly, they last much, much longer. A supermassive black hole with 1 billion solar masses would last about 10 to the 92nd power years. That's a trillion times longer than a stellar mass black hole. And the largest supermassive black holes, those that might contain trillions of solar masses after eons of mergers and accretion, would last even longer. A black hole of about 100 trillion solar masses, which is about as large as they could plausibly get, would have an evaporation time of approximately 10 to the 100th power years. 10 to the 100th power. That's a Google from the mathematical term coined in 1920 by 9-year-old Milton Sirota, the nephew of mathematician Edward Kasner. A Google is a 1 followed by 100 zeros. Let me try to convey what this number means, though I warn you that true comprehension is probably impossible. If you wrote down the number 10 to the 100th power in standard decimal notation, starting at the edge of a sheet of paper, with each digit being 1 millimeter wide, the number would stretch for 100 millimeters, about 4 inches. That doesn't sound like much, but the value that number represents is beyond astronomical. 10 to the 100th power is larger than the number of atoms in the observable universe, which is only about 10 to the 80th power. It's larger than the number of Planck volumes, the smallest meaningful units of space in the observable universe. It's larger than any number you could construct by combining physical quantities in any reasonable way. If you tried to count to a Google, counting one number per second, it would take you 10 to the 100th power seconds. The universe has only existed for about 4 times 10 to the 17th seconds. You would need to count for a time that exceeds the current age of the universe by a factor of roughly 10 to the 82nd power, and the largest supermassive black holes will take a Google years to evaporate. This is the timescale of the black hole era. Let's jump forward in time and watch this process unfold. Let's watch the last structures in the universe slowly fade away. 10 to the 50th power years. We're now far beyond the proton decay era. The universe has been dark and empty of ordinary matter for an inconceivably long time. If there were anyone to observe it, they would see nothing. Absolutely nothing. No light, no matter, no structure of any kind visible to any instrument. But the black holes are still there, scattered through the void. They're invisible, of course, absorbing any radiation that falls on them and emitting almost nothing. But they exist. They're the only significant concentrations of mass energy left in the universe. The stellar mass black holes, the smaller ones, are starting to show the effects of Hawking radiation. They've been evaporating for what seems like eternity, and they've lost substantial fractions of their mass. Some of the smallest ones, those that were perhaps 5 solar masses when they formed, have shrunk considerably. Their event horizons have contracted. Their Hawking temperatures have risen. This creates an interesting feedback loop. As a black hole loses mass, it gets smaller. As it gets smaller, its temperature rises. As its temperature rises, it radiates faster. As it radiates faster, it loses mass more quickly. The process accelerates. The smaller the black hole gets, the faster it evaporates. In the early stages, this acceleration is imperceptible. A black hole might take 10 to the 67th power years to lose half its mass. Then 10 to the 67th power years more to lose half of what remains. The timescales are so vast that the acceleration doesn't matter much. But as the black hole shrinks below a certain threshold, things change. The evaporation speeds up noticeably. The final stages of a black hole's life unfold much faster than the early stages. 10 to the 65th power years. The stellar mass black holes are in their final stages. They've shrunk to tiny fractions of their original mass, where once they contained the mass of 10 suns, now they contain perhaps the mass of a mountain. Their event horizons have contracted from kilometers across to meters, then centimeters, then millimeters. Their Hawking radiation is no longer negligible. They're glowing, getting warmer and brighter as they shrink. For the first time in eons beyond counting, these black holes are emitting significant energy into the void. They're becoming visible in a sense, though there's no one to see them. The final moments of a black hole are dramatic, at least by the standards of this dark and quiet era. As a black hole shrinks below a certain mass, its temperature rises dramatically. A black hole with the mass of Mount Everest would have a temperature of about 1 billion degrees. It would be emitting gamma rays, X-rays, visible light, every form of electromagnetic radiation. In its last second of existence, a black hole releases an enormous burst of energy. All of its remaining mass is converted into radiation in a final explosion, a cosmic firecracker going off in the emptiness. For one brief instant, there is light in the void. But here's the strange thing. From our far future perspective, even these final explosions are cold and dim. The universe has been expanding for 10 to the 65 power years. Space has stretched by an incomprehensible factor. Any radiation emitted is immediately redshifted, its wavelength stretched by the expansion of space. The brilliant flash of a dying black hole, which would have been blinding at close range, is stretched to wavelengths far beyond anything we could detect. It becomes a whisper of radio waves, then a murmur of even longer wavelengths, eventually fading into the background hum of an ever-expanding, ever-cooling universe. The black hole is gone, but its final cry is barely audible against the silence. 10 to the 67th power years. The last stellar mass black hole has evaporated. One by one over the preceding eons, they've all gone through their final explosive moments and vanished. Each one took away a small piece of the universe's remaining structure, converting concentrated mass energy into dilute radiation that dispersed into the void. Trillions upon trillions of stellar mass black holes formed in the supernova explosions of massive stars during the stelliferous era have now all evaporated. They endured through the death of the stars. They endured through the decay of matter, but they could not endure forever. Hawking radiation claimed them all, slowly but inevitably. But the supermassive black holes remain. They're far more massive and far cooler. Their Hawking temperatures are so low that they radiate almost nothing. They'll persist for eons more, lonely giants in an empty universe. Let's jump forward again. 10 to the 85th power years. We're now at a timescale that makes even the stellar mass black hole era seem brief. A time so far in the future that the entire previous history of the universe, from the Big Bang to the death of the last stellar mass black hole, occupies a negligible fraction of what has passed. The supermassive black holes are finally showing signs of decay. They've been radiating Hawking radiation for so unimaginably long that even their immense masses are beginning to diminish. Event horizons that once spanned light years have contracted. Temperatures that were once unmeasurably close to absolute zero have risen slightly. Some of the smaller supermassive black holes, those with perhaps 1 billion solar masses, are approaching their end. Over the eons, they've lost significant fractions of their mass. They've shrunk from monsters that dominated entire galaxies to more modest objects. Their Hawking temperatures have risen from essentially zero to measurable, if still incredibly cold, values. These black holes are warming up. Not in any way you'd notice, not by any standard that would seem warm to a human being, but warming nonetheless. They're preparing for their final dissolution, the last stage of their immensely long existence. 10 to the 95th power years. The smaller supermassive black holes are in their final stages. One by one, they're evaporating, releasing their remaining mass as radiation. Each one marks the end of a structure that once sat at the center of a galaxy, that once was surrounded by billions of stars, that once played a crucial role in shaping the cosmic environment around it. Try to imagine what these black holes have witnessed over their existence. They formed in the early universe, perhaps from the direct collapse of primordial gas clouds, perhaps from the mergers of smaller black holes formed from the first stars. They watched as galaxies formed around them, as generations of stars were born and died, as planets formed and life arose and civilizations rose and fell on those planets. They endured as the stars went out, as the universe went dark, as matter itself decayed into radiation. They sat alone in the void for eons beyond counting, the last witnesses to a universe that had once been alive with light and energy and change, and now they're fading. Now they're giving up the last of their mass to the quantum vacuum, particle by particle, photon by photon. Each one represents the end of a structure that has existed since nearly the beginning. Each one is a final farewell from the age of matter and energy to the age of emptiness. 10 to the 100 power years, a Google years. We've reached the end of the black hole era. The last supermassive black hole, the most massive and long-lived structure ever to exist in the universe, is in its final moments. This black hole might have once sat at the center of a galaxy containing trillions of stars. Over billions of years, it consumed millions of solar masses of material, gas and dust, and entire stars falling past its event horizon, never to return. Over trillions of years, it merged with other supermassive black holes as galaxies collided and combined. It grew and grew, becoming one of the largest concentrations of mass energy the universe has ever known. Over eons beyond counting, it sat alone in the void, radiating its mass away, particle by particle. The stars had long since died. The matter had long since decayed. The smaller black holes had long since evaporated. But this one remained, a monument to everything that once was, slowly dissolving into the emptiness. Now it's small, shrunk from a monstrous thing that once warped space-time across light years to something much more modest. Its event horizon has contracted from astronomical dimensions to something you could almost comprehend. Its temperature has risen from unmeasurably cold to merely incredibly cold. It's radiating faster now. The feedback loop is engaging. As it loses mass, it heats up. As it heats up, it radiates faster. As it radiates faster, it loses more mass. The process accelerates. In its final moments, the black hole enters a runaway phase. It gets hotter and smaller at an increasing rate. The radiation becomes more intense. For the first time in eons, significant energy is being released into the universe. The black hole glows, dimly at first, then brighter. It emits radiation across the electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. For one brief instant, it's the brightest thing in the universe, the only significant source of energy in an otherwise dark and empty cosmos. And then, in one final burst, it's gone. The last black hole in the universe has evaporated. Its mass has been converted entirely into radiation, a final explosion of energy that disperses into a void that no longer contains any significant structures. The event horizon, that one-way door in space-time that had existed for a Google years, is gone. The singularity, that point of infinite density that lay at the center, is gone. Whatever information fell into this black hole over its immensely long existence, whatever record of stars and galaxies and perhaps civilizations it contained, is released back into the universe, scrambled beyond any hope of recovery, encoded in the radiation of its final moments. The black hole era has ended, and what remains is almost nothing. The universe at this point, 10 to the 100 power years old, a Google years since the Big Bang, is filled with nothing but the thinnest possible bath of radiation. Photons from the last black hole's evaporation already redshifting as they travel through expanding space. Photons from all the previous black hole evaporations stretch to wavelengths far beyond anything we could detect. Neutrinos that hardly interact with anything, streaming through a universe that no longer contains anything to interact with. Perhaps some exotic particles remain, particles we don't fully understand. Perhaps there are electrons and positrons, the lightest charged particles, scattered incredibly thinly through space, waiting for chance encounters that might not happen for eons. But there are no stars, no planets, no atoms, no black holes, nothing you would recognize as a thing. Just an endless, homogeneous expanse of space, expanding forever, getting colder and emptier as it goes. All of it is at almost exactly the same temperature. A temperature so close to absolute zero that the difference is essentially meaningless. There are no energy gradients, no differences in temperature or density that could drive any process. The universe has reached something very close to thermal equilibrium, a state where nothing can happen, because there's no free energy to make it happen. This is the edge of the final era, the dark era, the era of eternal silence. And compared to what comes next, even the black hole era was an instant. Because the dark era doesn't end. It doesn't last for another Google years, and then transition to something else. It doesn't have a boundary or a conclusion. It goes on forever. The universe will remain in this state, or something very close to it, for all of eternity. 100 trillion years of stars. 10 to the 40th power years of decaying matter. 10 to the 100th power years of evaporating black holes. All of that, everything we've described, was just the prelude. The overture before the main performance. The brief introduction before the endless silence. The actual duration of the universe, from the dark era onward, is infinite. Not very long, infinite. Time stretches out before us without limit, and in all of the endless time, nothing significant will happen. The universe will simply exist, empty and cold and silent, forever. This is where our journey takes us. Past the death of stars, past the decay of matter, past the evaporation of black holes, into the final silence that will last for all of time. 10 to the 100th power years have passed. A Google years. The last black hole has evaporated in a final whisper of Hawking radiation. Its mass converted entirely into particles that dispersed into the void. And now, for the first time since the Big Bang ignited the cosmos into existence, the universe contains no significant structures. Let that sink in. No structures, none. The stars burned out trillions of years ago. The matter decayed into radiation over timescales that dwarfed the age of stars. The black holes, those final monuments to the age of matter and energy, have evaporated over spans of time so vast that even the decay of matter seems brief by comparison. And now there's nothing left. Nothing at all. What does this universe look like? It's almost impossible to describe because there's nothing to describe. Space exists, vast and expanding, stretching out in all directions without limit. Time continues to pass, moment by moment, second by second, though the concept of seconds has lost all meaning when there's nothing to measure time against. The universe persists, but there's nothing happening in it. Try to imagine absolute emptiness. Not the emptiness of a dark room, which is still filled with air molecules and permeated by electromagnetic radiation. Not the emptiness of interstellar space, which contains a few atoms per cubic meter and is bathed in starlight and cosmic radiation. Not even the emptiness between galaxies, which still holds traces of gas and the faint glow of distant stars. This is emptiness beyond anything we can truly conceive. The average density of matter in the universe at this point is so low that there might be one particle per volume of space larger than the entire observable universe today. The radiation that fills space has been stretched by expansion to wavelengths longer than any meaningful scale, carrying essentially zero energy. The universe is filled with an incredibly thin bath of particles and radiation. Photons left over from the evaporation of the last black holes, now redshifted to wavelengths that would make radio waves seem like gamma rays by comparison. Neutrinos that hardly interact with anything, streaming through the void without purpose. Perhaps some exotic particles we haven't discovered yet, remnants of physics we don't fully understand, and possibly, scattered incredibly thinly through space, some debris that escaped all the processes of decay. If proton decay didn't quite get every last atom, if some stable configurations of matter somehow survived against all odds, there might be rare particles here and there. Electrons and positrons, perhaps, the lightest charged particles. Iron nuclei, if iron turns out to be truly stable against proton decay, which some theories suggest it might be. But even if such particles exist, they would be spread so thin that finding two of them in the same region of space would be essentially impossible. The average volume of space per particle would be larger than today's observable universe. Each surviving particle would be utterly alone, drifting through an emptiness so vast that it would never encounter another particle, never interact with anything, never participate in any process. This is heat death. The term sounds dramatic, like death by fire or extreme temperature, but it doesn't mean that at all. Heat death is death in the sense of reaching thermal equilibrium. It's the state where every region of the universe is at the same temperature, the same energy density, the same entropy. There are no gradients, no differences, no variations of any kind. To understand why this is significant, we need to understand what drives change in the universe. Every process, every event, every transformation requires energy flowing from somewhere to somewhere else. A star shines because nuclear fusion in its core releases energy that flows outward into space. A planet has weather because the sun heats some regions more than others, creating temperature differences that drive air circulation. Life exists because organisms can extract energy from their environment and use it to maintain their complex structures. All of this requires gradients, differences in temperature, in pressure, in chemical potential. Energy flows from high to low, from hot to cold, from concentrate to dispersed. This flow is what makes things happen. Without it, nothing can occur. The second law of thermodynamics tells us that entropy always increases in a closed system. Entropy is often described as disorder, but that's not quite accurate. It's more precisely defined as the number of microscopic arrangements, consistent with a given macroscopic state. High entropy means many possible arrangements. Low entropy means few. A universe with stars and galaxies and complex structures has relatively low entropy. Those structures represent ordered arrangements of matter and energy. A star is an incredibly unlikely configuration, matter concentrated into a sphere with nuclear fusion happening at its core. The probability of such a configuration arising by chance is essentially zero. Stars exist because a gravitational collapse created them, not because a random chance assembled them. As time passes, those ordered arrangements break down, stars burn out, converting gravitational and nuclear potential energy into dispersed radiation. The concentrated energy of a star becomes the dilute energy of photons streaming off in all directions. Matter decays, converting organized atoms into scattered particles. Complex structures become simple ones. Concentrated energy becomes dilute energy. Each of these processes increases entropy. The universe becomes more disordered, more uniform, more thermodynamically equilibrated. This is the inexorable direction of time, the arrow that points from past to future, from order to disorder, from concentrated to dispersed. Eventually, entropy reaches its maximum possible value. There are no more ordered structures to break down, because everything is already as disordered as it can be. There's no more concentrated energy to disperse because everything is already uniformly distributed. The universe has reached thermal equilibrium. This is heat death, the state of maximum entropy, the state from which no further change is possible because there are no energy gradients to drive change. It's not hot and it's not cold in any meaningful sense. It's simply uniform, the same everywhere, forever. In this state, the universe is perfectly homogeneous at the macroscopic level. Every region is identical to every other region. There's no information to transmit because there's no variation between different places. A message would have no meaning because there's nothing to distinguish one location from another. There's no change over time because there's nothing that can change. The universe has reached its final state. But we need to be careful here. Heat death doesn't mean everything stops in an absolute sense. At the quantum level, fluctuations continue. The uncertainty principle, that fundamental feature of quantum mechanics that forbids exact values for certain pairs of properties, ensures that there's always some activity at the smaller scales. Virtual particles still pop in and out of existence, borrowing energy from the vacuum for fleeting instants before returning it. Random motions still occur at the quantum level. Time continues to pass, moment by moment. The universe isn't frozen. It's just that these fluctuations are completely random, carrying no information, doing no useful work, driving no macroscopic processes. Imagine an infinite ocean, perfectly still and perfectly uniform at the macroscopic scale. No waves, no currents, no variation in temperature or salinity, just water, the same in every direction to infinity. But at the molecular level, there's still motion. Water molecules are still vibrating, still bouncing off each other, still exhibiting the random thermal motion that all particles have above absolute zero. That molecular motion doesn't create waves or currents because it's completely random. There's no pattern, no direction, no organization. It's just noise, statistical fluctuations that average out to nothing on any larger scale. The ocean remains perfectly still, even though its molecules are in constant motion. This is what the universe will be like in the dark era. At the quantum level, fluctuations continue. But at any macroscopic scale, nothing happens. The fluctuations don't build up into anything significant. They're just random noise in an otherwise silent void. Let me try to convey what eternal means in this context, because it's profoundly different from anything else we've discussed. Throughout this journey, we've talked about enormous timescales, 100 trillion years until the last stars die, 10 to the 40th power years until matter decays, 10 to the 100th power years until black holes evaporate. These numbers are incomprehensibly large. They're so far beyond human experience that our brains simply can't process them in any intuitive way. But they're still finite. They still have an end. However large these numbers are, you could in principle counter them if you had enough time. They represent specific quantities, however astronomical. There's a moment when the last star dies, a moment when the last proton decays, a moment when the last black hole evaporates. Those moments exist somewhere on the timeline of the universe. Eternity is different. Eternity has no end. The dark era will last not for 10 to the 100th power years, not for 10 to the 10 to the 100th power years, not for any number you can write down, however large. It will last forever. The dark era is not a period with a beginning and an end. It's a state that, once reached, persists without limit. This is profoundly difficult to grasp. Our minds evolved to deal with finite quantities. We understand beginnings and endings. We understand durations. We don't understand infinity, not really. We can manipulate the concept mathematically, but we can't truly imagine what endless time feels like. Consider this. For every moment that passes in the Dark Era, an infinite number of moments remain. The Dark Era is no closer to ending after a Google years than it was at the beginning. It's no closer to ending after a Google years. It will never be closer to ending because there's nothing for it to be closer to. Eternity doesn't approach anything. It just continues. The Stelliferous Era ends. The Degenerate Era ends. The Black Hole Era ends. But the Dark Era doesn't end. It is the final state, the ultimate destination, the asymptote toward which the universe has been heading since the Big Bang. Once reached, it persists forever. This raises fascinating questions about what might happen over truly infinite time. Could something emerge from this void? Could quantum fluctuations, given unlimited time, ever produce anything interesting? In principle, yes. This is one of the most mind-bending implications of eternal time. Given infinite duration, any event with finite probability, no matter how small that probability is, will eventually occur. Not just once, but infinitely many times. Quantum fluctuations occasionally produce particles from the vacuum. This happens all the time, even now, even in the room where you're sitting. Virtual particles pop into existence constantly. Normally, they recombine and vanish almost instantly. But occasionally, under the right conditions, they can become real particles. In the Dark Era, with infinite time available, fluctuations will eventually produce more than just individual particles. They'll produce atoms. The probability of quantum fluctuations spontaneously assembling a hydrogen atom from the vacuum is unimaginably small, but it's not zero. And given infinite time, it will happen. Over even longer timescales, fluctuations will produce molecules, then complex molecules, then, given enough time, macroscopic objects. The probability decreases exponentially with complexity, but infinity is a long time. Long enough for essentially anything to happen. This leads to one of the strangest concepts in theoretical physics, something called Boltzmann brains. The idea is named after Ludwig Boltzmann, a 19th century physicist who made fundamental contributions to thermodynamics and statistical mechanics. A Boltzmann brain is a hypothetical self-aware entity that arises spontaneously from random fluctuations in a universe at thermal equilibrium. The idea is this: if quantum fluctuations can produce simple structures, and given infinite time they will produce complex structures, then eventually they'll produce a structure complex enough to be conscious. Your brain is, at a fundamental level, a particular arrangement of atoms. A very complex arrangement, certainly, but still just atoms arranged in a specific pattern. If fluctuations can produce atoms, and given infinite time can produce any arrangement of atoms, then eventually they'll produce an arrangement identical to your brain, complete with all your memories and thoughts and experiences. This sounds absurd. The probability of quantum fluctuation spontaneously assembling a functioning brain is so incredibly small that writing it down would be meaningless. It's not just unlikely in the way that winning the lottery is unlikely. It's unlikely in a way that transcends any comparison we could make. If you wrote the probability as a fraction, the denominator would be a number so large that it would fill more pages than all the books ever written. But infinity is bigger than any finite number. Given unlimited time, even this preposterously unlikely event will occur. Not just once, but infinitely many times. Over the infinite duration of the Dark Era, Boltzmann brains will spontaneously appear, exist for a fleeting moment, and then dissolve back into the void. This leads to troubling implications that physicists and philosophers continue to debate. If the universe will produce infinitely many Boltzmann brains in its eternal future, and only a finite number of real brains existed during the Stelliferous Era, then the overwhelming majority of conscious experiences in the history of the universe will be random fluctuations rather than products of normal evolution. Some physicists find this deeply problematic. If most conscious experiences are Boltzmann brains, then statistically, you should expect to be a Boltzmann brain rather than a real person. But Boltzmann brains have random disconnected experiences that don't match the coherent, continuous experience we actually have. This tension between prediction and observation is called the Boltzmann brain problem, and it remains an open puzzle in cosmology. There are various proposed solutions. Perhaps the universe won't last forever. Perhaps some process will eventually end even the Dark Era, resetting the cosmos or transforming it into something else. Perhaps our understanding of quantum fluctuations is incomplete in ways that make Boltzmann brains impossible. Perhaps the whole framework of reasoning about infinite time is flawed in ways we don't yet understand. But let's step back from these technical puzzles and consider what the Dark Era means for us, here, now, in this brief, bright moment before the eternal night. We exist in a privileged time. The Stelliferous Era, with its stars and galaxies and planets and life, represents an infinitesimally brief window in the total history of the universe. If you tried to represent all of cosmic time on a line, from the Big Bang through the Stelliferous Era, through the Degenerate Era, through the Black Hole Era, to the Eternal Dark Era, you couldn't do it. The Dark Era is infinitely long. Any line you draw would have to be infinitely long to represent it. And on that infinite line, the Stelliferous Era would be a single point at the very beginning, invisible at any reasonable scale. We exist during that point. We're alive during the cosmic instant when stars shine, when complex chemistry is possible, when matter can organize itself into thinking beings that wonder about their origins and their fate. This is staggeringly improbable. Of all the moments in the infinite history of the universe, we happen to exist during the only ones when existence like ours is possible. Think about what had to happen for you to be here, contemplating these ideas. The Big Bang had to produce matter with just the right properties. The fundamental constants of physics had to have just the right values for stars and planets to form. Stars had to live and die, creating the heavy elements that make up your body. Planets had to form inhabitable zones around stable stars. Life had to arise and evolve for billions of years. And finally, the particular genetic combinations that produced you had to occur. Each step in this chain was improbable. The whole sequence is almost miraculous in its unlikelihood. And yet, here you are, conscious, aware, able to understand the story of the cosmos from its fiery birth to its cold, eternal end. The Dark Era will last forever, but it will contain essentially nothing. No stars to light the void, no planets to orbit those stars, no complex chemistry to build molecules, no life to experience anything, just eternal emptiness, eternal silence, eternal cold, an infinite duration of nothing happening. Everything that matters, everything that can matter, happens during the brief periods before heat death. The Stelliferous Era, with its blazing stars and teeming planets and developing civilizations. The degenerate era, with its slowly cooling remnants, still containing matter even if that matter can no longer shine. Even the black hole era, with its evaporating monsters, still contains concentrated structures, still has something rather than nothing. The dark era has none of that. It's the ultimate equality, the state where everything is the same because there's nothing to be different. No information, no pattern, no structure, no significance, just space, expanding forever into an emptiness that will never be filled. This brings us to the deepest question raised by contemplating the end of time. What does all of this mean for us, here, now? Does knowing that everything will eventually fade into eternal silence make our lives less meaningful? Or does it somehow make them more meaningful? I believe it makes them more meaningful. And here's why. Meaning doesn't come from permanence. Think about the things that matter most to you. A beautiful sunset. A piece of music that moves you. A conversation with someone you love. A moment of insight when you understand something you didn't understand before. None of these things last forever. The sunset fades. The music ends. The conversation concludes. The moment of insight passes. But their transience doesn't make them less valuable. If anything, it makes them more valuable. A flower isn't less beautiful because it will wilt. A sunset isn't less glorious because it will end. A human life isn't less precious because it will conclude. Impermanence is part of what makes things valuable. If flowers lasted forever, we wouldn't pause to appreciate them. If sunsets never ended, we'd stop watching them. If we lived forever, would individual moments still feel precious? It's precisely because things are temporary that we notice them, treasure them, find them meaningful. The Japanese have a concept called mono no aware, which roughly translates to the pathos of things or an empathy toward things. It refers to the bittersweet awareness of impermanence, the gentle sadness that comes from knowing that everything beautiful will pass. But this awareness isn't depressing. It's what makes beauty possible. Without impermanence, there would be no beauty. Just eternal sameness. The universe is impermanent in the same way, not in the sense that it will cease to exist, but in the sense that its interesting phase is finite. The stelliferous era will end. Stars will go out. Complexity will fade. Eventually, eternal silence will reign. The cosmic story has a beginning, a middle, and an end, just like all good stories. But this doesn't diminish the present moment. It enhances it. Right now, stars are shining. Right now, galaxies are spinning in their ancient dance. Right now, planets are orbiting, life is flourishing, and consciousness is contemplating its own existence. This is happening. It's real. And it matters precisely because it won't last forever. You are here, in this brief cosmic moment, alive and aware and capable of wonder. Every star you see in the night sky is a gift of this particular era. Every thought you think, every emotion you feel, every connection you make with another being happens during this infinitesimally brief window when such things are possible. The universe has given you consciousness. Think about how remarkable that is. Out of all the matter in the cosmos, out of all the possible arrangements of atoms, some of those atoms came together in a pattern that can think, that can feel, that can wonder about its place in existence. The universe has become aware of itself through you. It has given you the ability to understand what you are and where you are in cosmic history. You know things that no being could have known during the early universe, when matter was too hot and chaotic to form structures. You know things that no being will know during the Dark Era, when matter no longer exists to form thinking minds. You exist in the narrow window when understanding is possible, and you've used that existence to actually understand. The universe has given you this moment, this now, this present instant that will never come again. The past is gone, dissolved into memory. The future hasn't arrived, existing only in anticipation. There is only now, this present moment, and in this moment you are alive, in a universe that is still capable of being alive. The Dark Era will come, the stars will go out, the atoms will decay, the black holes will evaporate, silence will fall across the cosmos and will never be broken. Everything that exists now will cease to exist. Everything that matters now will cease to matter. The universe will forget that it ever contained stars, planets, life, consciousness. But you are here now. And now is the only time that ever really exists. The Dark Era will last forever, but it will never contain a moment like this one. It will never contain stars shining and planets spinning and people wondering about their place in existence. Those things are happening now, only now, in this brief flash before the eternal night. This is the message of cosmic time. Not despair at the coming darkness, but wonder at the present light. Not fear of the ending, but gratitude for the beginning. Not mourning for what will be lost, but celebration for what exists right now. Look up at the night sky tonight, see the stars that are still shining. Know that they won't shine forever, that each one is burning through its fuel, that one day each will go dark. And know that you're seeing them now, in this moment, during this brief cosmic instant when such seeing is possible. The light from those stars has traveled for years, decades, centuries to reach your eyes. That light began its journey before you were born, and you're here to receive it. That band of light stretching across the sky, the Milky Way, contains 400 billion suns. Each one is a nuclear furnace converting hydrogen into light. Each one is a temporary structure, a brief arrangement of matter and energy that will eventually disperse. But each one is shining now. Each one is contributing its light to the cosmic glow that illuminates your night. The atoms in your body have been on a journey that defies comprehension. They were forged in the hearts of dying stars billions of years before Earth existed, scattered across light years by supernova explosions, drifting through cold nebulae for millions of years, slowly gathering into the disk of gas and dust that became our solar system. They've been part of mountains and oceans, of ancient creatures and forgotten forests, cycling through countless forms before finding their way into you. You are not merely made of stardust. You are stardust that woke up, looked around, and wondered where it came from. The story of the universe is written in your bones. Every atom of calcium, every trace of phosphorus, every molecule of water in your cells carries a history stretching back to the Big Bang itself. You are the cosmos experiencing itself, a temporary arrangement of ancient matter that has somehow become aware of its own existence and its own mortality. And someday, those atoms will continue their journey without you. They'll return to the earth, be taken up by plants, breathed by animals, washed into oceans, and eventually find their way back to the stars when our sun expands and dies. They'll drift through the degenerate era as the universe cools. They'll dissolve into radiation as protons decay. They'll witness the evaporation of the last black holes. The atoms that are you right now will be there at the end, scattered and transformed, but still part of the story, still riding the long, slow wave of cosmic time into the final silence. But that's not sad. That's beautiful. You're part of this grand narrative. You're a temporary pattern in the cosmic dance, a brief eddy in the flow of matter and energy, a momentary consciousness in a universe that will spend eternity unconscious. And you're here to witness it, to appreciate it, to wonder at it. The final silence is coming, but it's not here yet. The darkness will reign forever. But first, there is light. The universe will sleep eternally, but right now it dreams. And you are one of its dreams. So don't mourn the coming darkness. Celebrate the present light. Don't fear the ending. Embrace the moment. The universe gave you this brief, precious, irreplaceable experience of being alive and aware during the stelliferous era. The cosmic springtime, the brief, bright instant before the eternal night. Live it. Feel it. Be grateful for it. And when you look up at the stars, know that you're seeing something that won't last forever, but that exists right now. That's real. That matters. That's meaning enough. The final silence will come. Time will run out. Everything we know and love will fade into the endless dark. But not yet. Not today. Today the stars still shine. Today the universe is still alive. Today you are here to see it. And that, against all odds, is something rather than nothing. Thank you for joining me on this journey through time, from the present moment to the death of stars, through the decay of matter and the evaporation of black holes, to the eternal silence at the end of everything. If this exploration moved you, please consider liking and subscribing. It helps me continue making these journeys into the deep questions of existence. And tonight, when you look up at the sky, remember what you've learned. Those stars won't shine forever. The light you see has traveled across our years of empty space to reach you. And someday, no light will travel anywhere because there will be no stars to emit it. But you're seeing that light now. You're alive in the universe's brief, bright moment. You're conscious during the cosmic instant when consciousness is possible. You can see the stars and know what they are and understand where they fit in the story of everything. The universe will fall silent. But first, it spoke. And you were here to listen. Sleep well tonight, under stars that won't last forever. Know that you were here during the light, before the final silence. Good night.